This presentation is about power quality and new technologies, so it's a little bit broader than only EV, but I think also this combination of EV, PV and all other new technologies are quite important. Power quality, I think most of the people who are listening now will be acquainted with the most of the power quality phenomena, but to be sure, I will address some of them. The voltage dips, certain reduction in the voltage level due to mostly the short circuits in the network. And the voltage harmonics, distortion due to harmonic currents, mostly coming from nonlinear loads. The voltage fluctuations due to inrush currents, leading to fast voltage variations, also known as flicker, one of the most common problems for the grid operators in the Netherlands, but I suppose also in other countries. Over voltages, voltage level in general, of course. And when we look to these power quality phenomena, we also have to look to responsibilities. And when we look to responsibilities, mostly we look to the point of connection. So whereas the connection of the network of the grid operator to the installation of the customer, there we find the responsibilities of the grid operator, who is responsible for the voltage, the responsibility for the manufacturer, who is responsible for his device, his equipment, that it is not injecting too much inrush currents or harmonic currents or super harmonics into the network, but also has some immunity against voltage distortions. So there's always an interaction between the current of the installation and the voltage of the network operator, depending also, of course, on the impedance of the network. But at this point, the point of connection, we have the customer who is responsible for the total current of the installation, so the harmonic currents, the inrush currents, the normal load, that is not disturbing too much the voltage at the grid operator side. The responsibilities and also standards are quite important in this power quality field. When we look to responsibilities, you look to the network operators, you can maybe divide somewhere the responsibility of the TSO was mostly a national utility and responsible for the high voltage network. In the Netherlands, it will be the 380 kV, the 220, 150, 110 kV, and responsibility of the DSO, who was responsible for the low voltage and the medium voltage distribution networks. And what we see in the last decennia already, I think that the nature of the loads connected to the low voltage network and to the medium voltage network is changing. Of course, there are a lot of generation connected to the network. More and more solar system photovoltaic installations are connected to the low voltage network and the medium voltage network. But when you look to the size of the solar panels, solar systems, you already have solar plants of 15 megawatt, 100 megawatt, who are directly connected to the high voltage network. But you also have wind farms connected to the high voltage network, connected to the medium voltage network. So the load, the power flows in the network, what normally were from high voltage to medium voltage, from medium voltage to low voltage, are now also going from low voltage to medium voltage and from medium voltage to high voltage. So these power flows are changing. It's not only with production what is connected to the low voltage network and the medium voltage network, but it's also with the additional loads connecting to the network. Because when you look to new technologies, electrical vehicles is one example of it. More and more electrical vehicles are connected to the low voltage network, but also fast charging stations are connected to the medium voltage network. So there is a new loads, this electrical vehicles, but also the heat pumps. And that will also have some impact on the network for low voltage network, but also for the medium voltage network. But the whole nature of the installations is also changing. We are talking about the smart grids. I think the last, let's say 5 to 10 years, a lot of focus on smart grids. But now also the focus is shifting a bit to the smart installations. And at the end, maybe we don't need to speak about grids, or we don't need to speak about installations. We have to speak about the smart system. Of course, at the end, everything is connected to each other, and it has to work with each other. So when we look to the smart installations, you get installations where in houses you also have some production, you have maybe some storage, maybe you have on your site with a lot of customers together kind of storage, and also an energy management system, and maybe one connection to the electrical grid, combining installations of several households or several installations in a street or a region. So also the nature of the installations will change in future. And they could also contribute to the power flows control and voltage control in low voltage or medium voltage networks. So looking to the impact of DG, this distributed generation, or EV on voltage levels, for example, here see a situation of a medium voltage network drawn as a ring system, but somewhere there will be an opening because most of the medium voltage network will be operated in a radial way. There's at the moment mostly a control of the voltage at the transformer from high voltage to medium voltage. And then at the end, when you look to the low voltage network, in the low voltage network will be added some solar systems, increasing the voltage level at the end of the low voltage installation, because the energy has to go back from the houses into the network or to the other houses, of course. You will get an increase of the voltage level at the end of the cable here. But on the other hand, you will also have a decrease of the voltage level due to additional load, heat pumps or electrical vehicles. So the increase in the variation of the voltage will be quite high. During the day, there will be higher voltages due to the solar systems. In the evening, when electric vehicles are coming home, there will be an increase in voltage drop, so the voltage levels will be lower. The voltage level should be somewhere between 230 volts plus or minus 10%. This variation will be there due to the variation in load and production in the low voltage network, but also due to the variation in load and production in the medium voltage network. So this plus or minus 10% is somewhere a variation you have to divide in the medium voltage network and in the low voltage network. So maybe the plus or minus 5% you need for the medium voltage network, and then you have an additional plus or minus 5% for the low voltage network. Dus this impact of DG and EV on voltage level will be certainly be seen in the distribution network. One possible solution for this voltage variation is a smart transformer as part of the smart grid. And the smart transformer is a transformer who can regulate the voltage at the secondary side of the transformer, so you can keep the voltage at the low voltage bus bar at the same level. The variations in the medium voltage network, what is shown in blue, something you don't have anymore when you switch on the smart transformer. That means that the plus or minus 5% that you have kept for the medium voltage can also be spent in the low voltage network. So the full plus or minus 10% variation is something you can utilize in the low voltage network. So that's mostly a very nice solution for voltage variations in the low voltage network. But that's not the only one. Another possible solution is the curtailment of active power. So the moment that you reach somewhere the limit of the voltage in the low voltage network, you could limit the PV power what is produced at a certain level. It could be 70%, could be 60%, could be depending on the voltage. Or you could have a certain curtailment. As you say to every customer, you may not inject more than 70% of your maximum peak, but you could also look to the voltage level, and depending on the voltage level, you could reduce the active power what you inject into the network. Disadvantage of this one is that always the customer who is connected to the end of the cable is solving the problem. And in this case, you can solve the problem with all customers connected to the network. Another solution is reactive power. But reactive power is only working quite effective when the R divided by X ratio, R by X ratio is quite small. When you have a low voltage network with a lot of resistance, then this reactive power doesn't work very good, and also will give you more losses in the network because you are drawing more current. And you also need a higher apparent power of your inverter. But when you have a medium voltage network close to the transformer and the R over X ratio is higher, is quite small, then it could be a good solution. Looking to the EVs, because we are now looking to adapting the production, but you could also, of course, adapt the load, because at the end what you want is a balance between production and load. So instead of adapting the production, you could also adapt the load side. So increasing the load, so it could be done by smart charging, but you also could even deliver energy back. So even make from the load a production unit, so delivering energy back from the car to the grid. Another solution is storage. So when you have storage in your installation, and probably the amount of storage will increase in the coming decennia, you could also use this storage for balancing the production and load. So you need some energy management. Could also be something what could already be done on the site, because at the moment the storage is quite an expensive device, and only for balancing production and load it could be too expensive. But when you can also use it for other functionalities, then it could be maybe a business case. And these other functionalities are energy management, no break system. So the moment that there is a problem with normal supply, you could use these batteries also as a no break system. You could use it in combination with a harmonic filter. You could do something about reduction of voltage variations, maybe also protection against voltage dips. And you could use it as an MMM. And MMM is maybe not something worth saying much, but it's a money-making machine. So try to sell your energy on the moment on the market when the prices are good, or store the energy when you can buy the energy for a very low price, or maybe even a negative price. People who are also watching the presentation of Alex in the morning also heard about the inertia of the big energy plants and the frequency and the stability of the network, these rotating mass of these big energy plants is now needed to get the stability of the network. But when we get more and more renewables into the network, there could be a problem with this stability. So when we have less inertia and more renewables, we have to find another way to ensure this stability of the network. For this reason, we have introduced RFG codes, so requirements for generators. And these requirements for generators has somewhere take over the task for the big generators, also the solar systems or the wind parks should be able to respond on deviations in frequency or deviations in voltage. So when the frequency is going up, and that means that there's an overproduction, there should be a reduction in production. And the other way around, when the frequency is going down, the production should be increased, or otherwise the load should be decreased. So you have to give some requirements also for your generators, not only for the response on voltage and on frequency, but also on the capability to ride through voltage dips. When there is a voltage dip somewhere in the network, it should not be the case that all these renewable generators are disconnecting from the network. So they have to stay connected and should support the stability of the network. So the impact on voltage dips is quite important, also how they react on the voltage dips. Voltage dip in general is an important power quality issue because voltage dip could lead to a lot of losses in industrial installations. So requirements for voltage dips and the amount of voltage dip that could occur in the network is also in the Netherlands important topic. We have made a proposal for limits for voltage dips, and that's shown in these tables for the high voltage network and for the medium voltage networks. And we made some classification. In this area A, we assume that most of the customers who have done a little bit of effort to get a higher immunity against voltage dips, they don't have any problem with voltage dips in this area. In other areas, we have some limits, so 1.2, 1.2, and 0.4. That's the maximum amount of voltage dip that could occur or what should occur in the networks. Otherwise, some research has to be done why there are more dips than these numbers. For the medium voltage network, this 3, 4 as a maximum number of dips. Maybe you wonder why it is 0.4, because you could have a dip or you could have no dip at all. So it should be 0 or 1 or 2 or 3, but 0.4 dips, and it's some weird number maybe, but there's a 5-year average, because the number of dips during the several years are changing, and we have chosen a limit that is based on a 5-year average. That's why this 0.4 here. So the impact on the voltage dips, also when you look to the future networks, is something what is done some research on. So what is happening when we have less conventional power plants and we have more renewables? Probably the short circuit power could decrease, and that could also have some impact on the amount of the spread of voltage dips. So that's part of the research what we are doing at the University in Eindhoven, done by Roseby. Perhaps in tomorrow, Vladimir Tsuk will tell more about this research. Another research that we are doing is the impact on harmonics, because when we have a new lot of new renewables connected to the network, new technologies, and that is for renewable energy production, but also for electrical vehicles. It's very important to look to the harmonic content, harmonic currents that they are injecting into the network, what the influence is on the harmonic voltages at the point of connection. So what is injected into the network from these renewables or electric vehicles? What is the harmonic background? Was already there, and what is the impedance of the network? Because all these factors at the end are important for calculating the harmonic voltage at the point of connection. So it's not only the harmonic current from the load side or from the solar systems or whatever, it is also the harmonic background was already existing for all the other customers connected to the network. And the impedance of the network itself, and that's also not a constant value because net configuration could change, but also all the load that is connected to the network is somewhere in this impedance. So what is normally done by the TSO is that they give a whole envelope of possible impedances in the network, depending on state of the network, for all frequencies. So for the first to the fifth harmonic, the fifth to the 10th harmonic, and so on. And then the customer has to calculate with the harmonic current that he is injecting into the network, if he is still complying with the harmonic voltages, what may occur at the point of connection. That's for high voltage, but also for medium voltage and for low voltage is calculation what has to be done, and not in a detailed way as it's done for the high voltage, because when we look to the medium voltage network and the low voltage network, there are millions of customers connected to the network, and you cannot look to every customer what he is injecting and is complying with the standard or not. So there has to be done some research on what is at the end possible for harmonic injection, not depending on impedances, but just a simple table. What is possible? How could a single customer connect harmonic currents into the network? There's some work what is done also at the university by Stanislav Bebev on harmonics and how they contribute to total harmonic current flowing into the network and the impact on the harmonic voltages in the network. So that's important for all solar systems connected to the network, but also electric vehicles connected to the network. What is the harmonic contribution of these electrical vehicles? So modeling these EV chargers is something what is also done to have some idea about what is the harmonic content of the chargers. Not only when they have a clean voltage, because most of these chargers are tested with a clean voltage, then you have some idea about harmonic currents that they're injecting into the network, but also when there's harmonic background voltage, you should know how they react on some distortion in the network. What you normally will see is that depending on the phase shift of the voltage and the current, harmonic background voltage could increase the harmonic current of the charger, but it could also decrease the harmonic current of the charger. These harmonic fingerprints are important to get some insight in how the chargers are reacting on harmonic background voltage. And of course, the problem of the superharmonics. In the earlier presentation, Alex already mentioned the importance of doing research on these superharmonics. So harmonics in the field of frequency band of 2.5 kilohertz to 150 kilohertz. Regulation is limited at the moment, and we see that more and more, not only with the solar system, but also with electrical vehicles, injecting harmonics in the frequency band 10 kilohertz, 20 kilohertz, 40 kilohertz. These harmonics will interfere with harmonics of other devices. or will overload capacitors in the network, will give problems with the function of other devices. So this is indeed a very important field of research, and I think Tim will give also a presentation about it tomorrow. I already talked about, let's say, smart grids, but it's also about smart installations, and there's a new standard, IEC 6364/8-1, and that's about smart installations, smart systems. So that's how to connect the smart grid with the installations. And normally that standards for the installations focusing normally only on safety, maybe a little bit on practical, but not about efficiency, not about smart, not about reliability, not about active. So active in a way that you can communicate with your grid and respond on voltage changes or frequency changes. So in these new standards, we are focusing also on other topics. 8.1 is about efficiency, but there's also a standard about 8.2, 8.3, but it's focusing more on smart and active. So the 8.1 is more about efficiency, but there we also see that there's a link with power factors and with harmonic currents and harmonic voltages. So there's also a link with all kinds of power quality phenomena. There's also a classification made, so you can build an installation and you can get a certain label from very efficient to very inefficient. And to get a very good classification, you have to look to a lot of interesting design points in your installations. I have just picked a few of them who have some relation with also power quality. And that's the power factor. So depending on the power factor of your installation, you can earn some points, and how more points you get, how more you will go to the best and the most efficient installation. Mostly in the grid code is already said you should have a power factor of 0.85 or more. So when that's not the case, of course you don't get any points, but when you have a very high power factor, you get the highest level of points. There's also for total harmonic distortion in the current. When you can reduce the harmonic distortion in the current, you get more points, so more efficient installation. And there's also the case for the total harmonic distortion in the voltage. Could a little bit discuss about this because you have already a harmonic background distortion in your voltage and you are not really responsible alone for the harmonic distortion in the voltage. But that's how this in this moment in the standard. So at the end, when you look to smart grids, you can think about smart grids. You can look to smart installations. I think we should not think in this way that we only look to smart grids or only look to smart installations. At the end, everything has to work together. So we have to look to how can we build the smart system, not only from installation, from customer point of view or from grid operator point of view, but how can we build this together? So that's my presentation about power quality and new technologies. Thank you for attending this meeting, and now perhaps there are some questions.
Yes, thank you, Sjef, for your nice presentation. I think you gave a very nice overview of what power quality is all about at the moment. I have a question myself. Do you feel that the power quality is getting more important in the future or compared to the last years?
Yeah, I think there's some reasons for that. I think there are more and more disturbing loads connected to the network. So let's say when you look to the emission side, you get more and more heavy loads which are non-linear, which are giving some distortion in inrush currents and the harmonic currents injected into the network. And from the other side, these new technologies are quite fancy, but also the immunity against certain power quality disturbances is maybe a bit lower than we are used to it, as I say, the old technologies in the past. So that's working two sides, and this from one side maybe a little bit more disturbance, and from the other side the immunity against the disturbance in the voltages are maybe a little bit decreasing.
Okay, thank you. Let me see. There's another question from Shamista from Ainexis about the smart transformer. She asked when there's a non-homogeneous load on a feeder, so for example you have one feeder with PV, another one without PV, is it still a good option to use the smart transformer then?
No, I think it is. This transformer will give you a lot of increase in the voltage variation what is possible in the low voltage network. Normally you have to calculate with plus or minus 5%, maybe plus or minus 6%, taking into account also the variation in the medium voltage level. So it gives you at least an increase in the possible voltage variation, even when you have load and production in different feeders. It will help you. You could, depending on how you put the setting of your transformer, you could set it on a stable voltage of 230 volts, but you could also change this setting depending on the moment of the day. When you use smart meters in your network, you can have some idea about the voltage levels in your network, depending on this lot of production or a lot of load. You can also change the setting of your transformer. That at the moment that you have in the evening maybe a lot of loads, you can put the voltage a little bit higher, and on the moment that you have a lot of production over day, you could put the setting a little bit lower. So combining it with smart meters, yeah, I think that will stay a very good option.
Okay, thank you. Let me see, we have time left for one more question. There's one question from Amir Broshi. Can you please explain the regulatory status of the IEC standard about efficiency?
Yes, this standard what is now relieved in IEC and Senelec. I think there is translated in the Netherlands, and we have the duty to make this part of the regulation within 2 years. So when it is relieved in Senelec, then we have to, within 2 years, we have to make it a standard in the Netherlands. This translated, and I had the idea that it somewhere in October, somewhere in let's say in a few months, it should be a standard in the Netherlands. So this is coming close to the introduction.
Okay, thank you. Let me see, there are a lot of people saying thank you for the presentation. I have another question from Shamista. Can you explain a bit more about the limit of the THD-I, so the current THD for installations?
Now, principle are not really, I think, limits for the installation yet. That's one of the problems. There are limits for devices and are standards for devices. Within Netherlands and within Europe, we don't have limits on the point of connection for the customers. So that's something we have to work on. For the total harmonic distortion, yeah, that's not really a limit. So I think, yeah, that's something we have to work on. When you look to this classification, the standard, they have chosen some values to get, let's say, efficiency. So they only look to losses in the network and not to the, at the end, to the impact on the voltage. That's something that, from grid operator point is also quite important. So yeah, what to say? At the moment, there are no limits, and we have to work on it. And that's, I think, also a part of the work that we have to do together with the regulator.
Yes, indeed. I think that's an important conclusion to make. Okay, I think that's it for now. Again, thank you for your presentation.